We might not notice, but tremendous technology and mind-boggling science constantly surround us in the products we use every day. Behind their practical use lurk hidden histories, dramatic discoveries, and awesome experiments. They are wicked inventions. Coming up, the Backhoe Loader. We discover what the iconic letters JCB actually stand for. Bridges. The science that explains why suspension bridges vibrated to destruction. Skis. Hunting, soldiers, the Olympics and aerospace. We reveal the amazing origins and materials that lie behind these snow-gliding wonders. We reveal the surprising science and amazing manufacture behind these wicked inventions. A backhoe loader is a large, heavy vehicle that consists of a tractor-like unit with a shovel or bucket and backhoe attached. Surprisingly, the backhoe name refers to the action of the shovel rather than the location of the loader. But just how was this earth-moving essential introduced?
In 1947, the Wainwright Corporation in Massachusetts developed a kind of hydraulic slew which could be attached to tractors, to trailers, and they started to produce these in quite small numbers.
This first development slowly progressed and was finally patented by the Wainwright Corporation themselves just a year later. This product could be mounted onto the back of trucks and other types of larger vehicles already invented.
On the first occasion, it was attached to a Ford A10 model truck bought by the Connecticut Light and Power Company. So it was put into kind of like the public sector and used with things like that.
Many then copied this method, using both trucks and smaller tractors to attach their backhoe loaders. However, from start to finish, this process took quite a long time.
Now, over in the UK at this time was good old JCB, and in 1953 JCB patented the first integrated backhoe loader, so a piece of machinery which was actually built purposefully for the use of excavation. So in about the mid-60s, JCB developed their first integrated backhoe loader. I think it was the first one in the world. It was the first time when the purpose of the machinery was completely for excavation rather than just being another addition. JCB, which was a company formed by Joseph Cyril Bamford, he's actually the only non-US person to be in the American Hall of Construction fame, so quite a big achievement.
The swivel chair was the next addition to JCB's loaders, which the company later patented and still feature in today's modern machines. These efficient improvements make the backhoe loader the wicked invention that it is. But just how are they made today? JCB are famous around the world for producing heavy-duty vehicles, often found in an iconic shade of yellow. One such vehicle is the backhoe loader, which has lots of different attachments for its rear arm, which can perform many tasks faster than a human being.
JCB was founded in 1945 by Mr. Joseph Cyril Bamford, JCB, and fundamentally is created since then revolutionary and innovative products all the way through until this day as we speak today.
The process begins with large sheets of steel plate. They are lifted onto a profiling machine which uses intense lasers to cut out a series of parts with high levels of precision. The parts are then separated from the offcuts, which is recycled to ensure an environmentally friendly process.
We can use up to 250 tonnes worth of steel which goes into the machines, ranging from 6mm plate to 20mm plate.
Next, the parts get prepared in a variety of ways depending on their use. They can be bent and formed into different shapes, which give them different strength properties. Parts can also have their edges nibbled or chamfered. This is the process of putting a specific edge on the metal to create, for example, smooth corners. The components for the chassis, loader arms, dipper, boom and more are all welded together in 3 stages. First, an operator will manually clamp the parts together in a jig and tack weld them. This process is designed only to hold the components together until they can be thoroughly welded later by a machine. Second, the components are cleaned up so that the tack welds are smooth and every joint edge is flush. Finally, the parts are loaded into a machine which takes them into a special area where the final welds are completed. With each backhoe weighing approximately 8.5 tons before it's picked anything up, the welds need to be very strong. The chassis is the skeleton that supports every other component, so it's crucial that it is as solid as possible. With the welding complete, the components then move on to the paint plant. Here, every fabricated component from manufacturing is shot blasted. This is where tiny particles are projected at the parts at very high speeds. The particles hit the components and take off the top layer of metal, revealing a clean layer beneath, which is a base ready for painting.
During that shot blast process, it's two iterative processes. One is to take off the poor surfacing of the material, and then secondly to dress the welds and clean all the welds up, which then goes into a phosphate, which then creates a preparation for two base coats of paint.
The painting process sees the parts get covered in the base coat of paint and travel through a drying room.
Sub-assemblies effectively then build up the axles, the engines, the transmissions. Then that crosses over from one of our assembly lines onto our main line.
On the main assembly line, the painted chassis has all the components connected to it. The complex hydraulic systems and electrical wiring loom is first. These supply pressure to all the pistons and data or power to all of the electronics. After each assembly step, records are updated to show exactly what the progress is for each vehicle. Next, the engine is dressed in all the external equipment. From belts to gearboxes, everything is securely attached. A crane is used to move heavy parts, such as the engine and rear axle, and hold them in place whilst they are secured. Next, more components are added, from the boom and scoop to intercoolers and pistons. Some parts, such as the cab, come from internal suppliers and only need connecting to the vehicle systems. The cab is lowered to about 30 centimeters above the chassis so the electronics and hydraulics can be connected. Then the cab is docked and secured. The backhoe arm is then fitted, along with any extra equipment ordered by the customer. The classic chunky tyres are fitted last, using a special tightening sequence to ensure the tyre is flush with the axle.
We also now, in terms of our attachments, have an infinite amount of capability and versatility to the machine to provide the market with a number of attachments, whether that be road sweeping, whether that be potholing.
After being filled with fluid to operate the hydraulic systems, the backhoe loader is put through a hot test to simulate the kind of stresses it would be put through by the customers. Every element is tested thoroughly, and if the machine passes, it moves on to PDI, or pre-delivery inspection. In PDI, the vehicle is thoroughly checked to make sure it meets the customer's specification and is fit for use. After a final sign-off, the backhoe is loaded onto a lorry and dispatched to work sites all around the world. The backhoe loader. Truly a wicked invention. We probably take them for granted, but these majestic feats of engineering allow us to traverse difficult terrain with ease, getting from one point to another in the most direct route possible. Where would we be without the bridge? The George Washington Bridge that connects the US city of New York to Bergen County, New Jersey, is considered the world's busiest bridge, with 102 million vehicles passing below its two towers every year, and is a far cry from the first bridges. These were probably little more than a plank of wood suspended between 2 points and would have had pretty apparent limitations.
The long flat plank gets quite weak towards the middle, especially if you put a high load on it, because all the stress is directed right across the beam. And so it's a weak point because the two supports act as a fulcrum, and so you can quite easily break whatever it is, especially if it's a wooden bridge which will flex and naturally bounce. And if you have people moving across it, the Romans recognized, on wooden bridges especially, that people don't march in step, because otherwise you generate harmonics and the bridge starts to bounce, and sympathetically the bounce gets stronger and stronger until the bridge breaks because people walk across it.
Luckily, the Romans were arguably the greatest bridge builders in antiquity and employed an ingenious structural form to make their bridges as strong as possible. Needing to transport goods, people and water to fuel their territorial expansion, the Romans used the arch as the basis on which to build the colossal bridges and aqueducts that crisscross their vast empire.
The reason an arch works very well is quite simple. You have a support that's quite a distance apart, and the arch transmits the energy down the arch itself and to the points where it needs to be, where the supports are. This transmission of the energy down into the supports works because the supports themselves are typically made of stone, and if the supports are made of stone, you can put pressure on either side. The stone is incompressible and won't move, and that pressure that's lateral pressure can also transfer the weight down into the ground at the point where you want, but allow also the ability for anything that's underneath it to go through.
While stone arches could transform the size and strength of bridges, they were a great deal more complicated to build, with the sides of the arch unable to support themselves until a wedge-shaped stone was placed at its apex. Appropriately named the keystone, this stone locked all the other stones in place, preventing the sides from collapsing and allowing the bridge to bear weight. This innovation led to greater spans between supports, which had added benefits.
For example, if you had to have relatively closely spaced supports, and it's a river that has a tendency to flood, what it means is you're restricting the river at that point, which puts a lot of force against the bridge and can cause it to collapse. If you have a wide arch, for example, then a lot more water can flow through it. You don't have issues with logs and other detritus jamming up and putting more pressure and overwhelming the bridge and causing it to collapse. So it's actually a vital means to make sure that a bridge doesn't collapse, yet is actually stronger. And if you use an arch, you can make it not only stronger, but also more lightweight, which means you can make bigger arches and you make bigger bridges.
Suspending a bridge is another key development in bridge design. The main forces in a suspension bridge of any type are tension in the cables and compression in the pillars. In a suspended deck bridge, cables suspended via towers hold up the road deck. The weight is transferred by the cables to the towers, which in turn transfer the weight to the ground. A deck suspended by cables allows for longer spans to be crossed, with less materials used and a smaller profile created. At just under 2 kilometers, the Akashi Suspension Bridge in Japan possesses the longest single central span in the world.
One of the benefits of a suspension bridge is that you can have it relatively low, but it can also be strong because the supports themselves act to hold one another in place. Each support has a cable running from one to another. That allows for flexibility of the bridge. It allows for it to sustain high winds without falling over, and a lot of that is a benefit.
One of the reasons a suspension bridge is so successful is that it is designed to be able to move. This is to accommodate changes in temperature, wind and load, which could otherwise destroy the bridge. In 1940, the US Tacoma Narrows Bridge in Washington state spectacularly destroyed itself because it moved too much, which was caused by something called resonance. Resonance is the tendency of a structure to oscillate or move at larger amplitudes at certain frequencies, known as the system's natural frequencies. At these frequencies, even relatively small periodic driving forces can produce larger and larger vibrations because the system stores energy.
As air passes over the cables that were holding the bridge up, they vibrate. This is normal, this is expected. What wasn't expected was that those vibrations and the bridge design was such that the vibrations of the ropes transmitted a vibration into the bridge. The problem with this bridge was it has a harmonic resonance frequency that was related to the distance of the ropes. So what that meant is that as a very small breeze occurred, a very large undulation started to happen in the bridge itself. As the wind got more powerful, this vibration became more sympathetic, meaning that it kept resonating and kept growing and growing and growing, at which point it turns, cracks, and breaks apart.
The Tacoma disaster led to a better understanding of bridge dynamics and the creation of safer bridges today. The bridge is truly a wicked invention. Can an egg take a surprising amount of weight? We all know an egg can be easily broken when we crack it on its side, but how strong is it if we change its orientation? For this egg experiment, we're going to need some eggs, 8 plastic bottle caps, and some bricks. We take an egg and rest it on an upturned bottle cap. We then place another bottle cap on top of the egg and repeat until we have 4 capped eggs. We take a 2 kilogram brick and gently rest it on top of the eggs. No breaks. Let's add more weight. 3 more bricks and still no breakages. Time to use some weights. In the end, our humble collection of shells manages to hold an amazing 32 kilograms before its surface finally shatters. The secret behind the eggshell's super strength is its shape. As we have seen, an arch is one of the strongest structures for bridges, and the egg uses the same curvy characteristics to its advantage. The curvature of the shell means the egg distributes the weights of the bricks and the pressures they apply evenly across its entire structure and minimises stress and strain. Can an egg take a surprising amount of weight? Yes, it can. Wicked challenge smashed. Quite literally. Skis have been used for travel across snow for millennia. However, in more recent times, they have been an essential for winter sports, leisure and fun. But just how were they introduced?
We've probably been skiing since about 6,000, 7,000 BC. It's one of the oldest kind of modes of transport, one of the oldest sports. It's also had martial and military implications. Skis back then, when we're looking at, thousands and thousands of years ago, wouldn't have really resembled the kind of polished foam designs we have today. Skis back then would have been shorter, a lot broader, a bit more like a snowshoe.
Despite not seeing many changes over the years, skis were introduced in a military capacity. Around 1200, during the Battle of Isen, not far from Oslo, the Norwegians were known for their fast and efficient travel over snow. In the course of the following centuries, we also saw Swedish troops adopt this method of transportation, increasing its use even further.
Now, the evolution of skiing really did follow some other technological advancements. So alpine skiing, which relies on people going very fast down a hill, started to become more popular with the invention of things like ski lifts, so obviously with pulley systems and the ability to kind of create all this stuff across mountains. So that was really about the kind of like later part of the 19th, early 20th century, but we start to see ski resorts opening up.
During the early stages of the 20th century, we saw the introduction of the television, which allowed many to watch the fairly new Winter Olympics. These Winter Games only elevated the popularity of skiing, as many watched on with excitement. Not surprisingly, a large amount of this audience liked what they saw, as sales of skis rocketed.
Nowadays, skis are what they call parabolic skis. They've got a slight lip on the front, which means you can go faster, they last longer, and they're also cheaper to produce.
From their hunting and survival basics to an Olympic necessity, skis really are wicked inventions. But just how are they made? Salomon have been creating ski equipment in the French Alps since the late 1940s and know exactly how to get the best out of a pair of alpine skis.
So Salomon's been born in the French Alps here in Annecy since 1947. When we started working with retailers, we introduced the ski in the early 90s, and it was a big success because we were doing something that was very innovative and something that was new to the market. Nobody was building the skis the way we were.
The production of a Salomon alpine ski begins with extensive market research that allows the company to create a ski that suits the needs of professional alpine skiers.
But the idea doesn't come from us. It's a variety of ideas. It's meeting with retailers, it's meeting with consumers as well as athletes to bring something to the consumer that is unique.
Once satisfied with their research, they can then move on to the design process. Here, the designer takes this research and begins to create the aesthetic design of the ski, using a combination of hand drawings and then three-dimensional computer designs on computer-aided design software, better known in the business as CAD. With the designs complete, the real ski building process can begin. Using wood core machinery, the raw wood is cut and cored out to shape. One machine creates the shape and another handles the thickness curve of the wooden core. Skis are built up in layers. Each of these layers are made up of different materials, such as fiberglass and rubber. both chosen for their flexible properties and enforced by the base.
So obviously in the ski, other than just a wood core, we have a lot of components. And when we work with these components, whether it be an aerospace technology called Coroid or maybe our patented CFX technology, these materials are brought in-house. We then have to specifically shape those or cut those to fit into the areas in the ski.
These layers are shaped with a cutting device that uses a press and steel blade that will actually cut out the correct shape. The edges of the skis are then formed. This is achieved by hand. They are first sandblasted and then bent to shape. The all-important pressing process is next. This is where all of our separate components are fitted together, much like a sandwich. All of these components are put into a ski mold, which is then placed into a press, which applies high pressure to our component sandwich, as well as heating it up at the same time. The goal here is to form a perfect bond, which the combination of pressure and heat will achieve. This particular ski contains many different components, including the ski tip and tail protector, wooden core, and layers of dry fibres, such as fiberglass, to name just a few. This is all helped along with the use of epoxy resin within the layers that will ensure an extremely solid bond. Now that the pressing stage is complete, our skis are really taking shape. The next stage is the rough finishing of the skis. This is where all of the excess epoxy resin and fibres around the ski are cut away. These excess materials are first trimmed, then the sidewall of the skis are milled. Once milled, they are then ground down by hand. With the rough finish completed, it's time for the all-important final finish. Using stone grinding methods, specific shapes and structures are ground into the base of the skis. This will give the skis the best possible glide on all of the different types of snow an alpine skier may face. The steel edges of the skis are then tuned. This is again achieved in a milling process, where two different angles are milled into the steel to create a sidewall angle and base side angle that will give the skis fantastic grip and great ski-to-snow contact.
Obviously, when you're skiing in an outdoor environment, you can come into contact with a variety of different materials, rocks and things like that. So we need to make sure that the edges are strong and durable. So with that, we need to make sure that we provide a specific process, but at the same time anchor it directly inside the ski to make it as strong as possible.
That's the build of our skis complete. The only thing left to do now is to take them to the testing laboratory. In the testing lab, flex tests, measurement tests and deformation tests will all ensure that the ski is performing exactly how it was envisaged back in the research and development stages. These tests will also show Salomon exactly how much strain and pressure their skis can withstand.
So the building of a ski process is one that's very long. It generally takes anywhere from 3 to 5 years, let's say, from the initial idea.
With the tests all passed, the skis are ready to hit the snow. Now that's a wicked invention. So, there you have it, a dash through the hidden history, super science and amazing manufacture of products that you use every day, but have never realised their amazing backgrounds. The Backhoe loader, bridges and skis, all wicked inventions.